welcome back to Daniel's Security Academy. Today is the first session I will try to approach the session itself a little bit different because before I usually had like kind of script what I want to say and started to just read it out. So today I just trying to be more relaxed and do just a bit more freestyle. We are going to talk about digital signature algorithm, DSA, to pretty much close off the asymmetric encryption topic we started in the past session. And we will also take a very deep dive into DSA and every single cycle of it. So yeah, this time we will not do a recap of asymmetric systems in general again. So if you need some more background information about asymmetric encryption systems in general, feel free to review the previous videos. In this session, we will get an overview about DSA and pretty much the four operations in there, which is key generation, key distribution, signing, and lastly a verification. And for each operation we go through the math and calculate our own example, and at the end we have a short summary describing all three asymmetric systems, so the two from the last time, Diffie-Hellman, RSA, and DSA from today. Okay, so DSA is also based on the public key cryptography system, just like Diffie-Hellman and RSA. So it's based on a pair of keys, public and private key. DSA focuses on digital signatures and signing off messages in general. And it is like the key rival to RSA. Which is also being used, also being good for use for digital signatures. So they kind of like are comparable algorithms in terms of signature. You cannot really compare DSA to Diffie-Hellman because Diffie-Hellman has a different focus point usually. Okay. DSA provides message authentication, integrity, and non-repudiation. So for this one, we just need to recall from the first sessions where we talked about the key principles in IT security. So for integrity, ensure message is not being altered. Non-repudiation, the sender cannot tell, okay, I didn't send it, it wasn't me sending it, and also on the other hand, the receiver cannot tell, oh no, I've never received it. So yeah, that's pretty much what we have also learned in the first, was it the first or second video? I'm not too sure. And as I just said, it has 4 steps in general in terms to operate, which is the first step was just the key generation, where we generate the key pair, the public and private key. Then we have the key distribution, so we need to get our public key out to the necessary people or clients, however you want to call it. And third step is, as a sender, you need to sign a message. And in order to verify this, we have the fourth operation, which is the signature verification step, which the receiver is doing. So yeah, let's take a closer look on how the process would look like in detail, just as we did it also with the RSA algorithm. So yeah, expect some deep math in here. The first step is, so we are in the key generation phase, right? So it's the first operation in DSA. And in order to generate the keys, we need to choose an approved hash function, which is H, and such an approved hash function would be, for example, SHA-2, And down in this example, on the right hand side, you will see the example. We choose SHA-512. Then we need to choose a key length, which is L. A recommended length is 2048 bit, which we also just use because it's the recommended length. Then we choose the modulo length, N. Pair of N and L exist as a recommendation. So meaning if you have the key length L of 2048, we recommend you using the modulo length N of 256, for example. So in our example, we pick N as 256. Then we choose a prime number which is of the length N bits, so 256 bits. Since 256 bits is quite a huge number, for example, we stick with Q as 11, so it is a little bit easier to follow the calculation. So yeah. Then we pick another prime number. Oh, sorry, I think I didn't mention that. So Q needs to be a prime number, just as P, and P is supposed to be of the length of L bit, so pretty much up to 2048, and P must be P minus 1 as a multiple of Q. So we have pretty much the equation on the right hand side under 0.5, which is P minus 1 modular Q, supposed to be 0. And we just plugged in the number 23. This is the preferred number I want to use as the prime number for P, and this is to verify and validate it. We run the numbers, so which is 23 minus 1, which is essentially 22, modulo 11. So 22 modulo 11 is 0. Oh, means P as 23 works just as fine. And then we have to choose an integer h, so small h, randomly, which must be bigger than 2, but smaller than P minus 2. And in our example, we just pick 5. So 5 is bigger than 2 and still smaller than P minus 2, which is 21. So then we have to compute G. G is, if you take the formula on the bottom left, this is h times P minus 1 divided by Q modulo P. So let's plug in the numbers. For h we have 5, so it's 5 times. P minus 1 is 23 minus 1 divided by Q. Q is 11, so it's 5 times 23 minus 1 by 11. Modulo 23, which essentially comes up with 5 to the power of 2, modulo 23, which is 25 modulo 23, so the end result is 2. G is at the end 2. Now, if you thought we are done with the first phase, you are wrong. Now we actually need to compute the key pair. So to do so, we needed G as the final number, and we continuously need the two prime numbers Q and P. So for the next step, which is choose an integer x, small x, randomly, whereas x must be bigger than 0 but smaller than Q. So anything between 1 and 10 pretty much works. In our example, we pick 5. Then we need to compute y, which is g to the power of x modulo p. Plugging in our numbers, g we just calculated before, it's 2. then for x we just have picked 5 and run it modulo 23, which is like 32. So if you take 2 by the power of 5, it's 32 modulo 23, sorry, which ultimately is 9 as a result. And then we pretty much already have the numbers we need for the next phase. So the private key is the list of P, Q, G, and X. So X we just picked. This is our private key. So our private key is 23, 11, 2, 5. The public key on the other side is also P, Q, G, but you have Y as a fourth value. So our public key is 23, 11, 2, 9. And yeah, this is pretty much our key pair for the moment, which we can now use to sign and encrypt messages. However, before we can do so, we actually need to distribute our public key to the intended receiver, so he can verify our signature in general. So we need to publish our public key, which is Y, and we send it to the receiver. And the sender or the signer, no matter how you want to call him, he or she needs to keep the private key X secret at all times. So pretty much putting it into like the local key management safe, where the operation system pretty much takes the responsibility to do so. So now we get into the signing process. So the sender wants to send a message to the receiver, which is supposed to be signed by him. I have just put up the numbers we need for this calculation on top of the right side. So you don't have to look up the numbers or try to remember the numbers we had before. So, okay, for signing it, our first step is to choose again an integer small k randomly, whereas k needs to be bigger than 1 but smaller than q minus 1, as q is 11, so it must be between 2 and 9. So we pick k as 3. Then we need to compute small r, which is g to the power of k modulo p modulo q. When we plug in our numbers, we have in the brackets 11 to the power of 3 modulo 23, which is at the end 1331 modulo 23, which ends up 20. So we have 20 modulo 11 being 9. So r is 9. Now we need to compute small I, which is k times I modulo q, supposed to be equal to 1. So we have the equation 3 times I modulo 11 equal to 1. And if we plug in the numbers, you can fairly easily see that I must be 4. So 3 times 4 is 12. Modulo 11 is 1. So the next one is S, which we need to compute, which is I times big H plus X times R modulo Q. Also here we try to plug in the numbers, and let's take it from bracket to bracket. We have I as 4 times big H, which is 3, which we just have picked before. And we have X, which is our private key, which is 5, times R, which we just calculated, is 9. So we have pretty much 3 plus 9 times 3 plus 5 times 9, and make sure to do the calculation correct. So it's 5 times 9, which is 45, plus 3. So it's 48 in the bracket. So 4 times 48 is 192. Modulo 11 comes up to 5. So our signature is now R and S, what we just have calculated, using our prime numbers and using our private key, pretty much. So our signature is 9 and 5. When the receiver gets the message, which is signed, the receiver has the signature and has the public key. So, and also, for example, sure, the message itself and the hash of the message. So we need to verify that R is bigger than 0 and smaller than Q, and S is bigger than 0 and smaller than Q. So R is 9, meaning it is smaller than, it's bigger than 0 and is smaller than Q, which is 11. Same for S. S is 5, which is bigger than 0 and smaller than 11. So this one works. Check mark on this one. Then we need to compute the next variable. Yeah, I know, we have quite a lot so far already. I haven't counted actually, but yeah. So now it's W, which is S times W modulo Q equals 1, which is very same equation as we had for the signing process, where we had I as the variable. So plug in the numbers. We have 5 times W modulo 1 equals 1. And for this one, it is we need to go a little bit higher in the numbers. So W ends up to be 20. So 5 times 20 is 100. And 100 modulo 11 is pretty much like 99. Modulo 11 is 0. So we have the rest of 1. So 100 modulo 11 is equal to 1. Now we need to compute U1, and yes, we will have U2 as well. And U1 is pretty much the hash of the message, so big H of M, times W modulo Q. So this is pretty easy to calculate. We just plug in the numbers we have already. So there's nothing we need to find in the equation itself. So it's 3 times 20 modulo 11. So 60 modulo 11 is 5. Now we have U2, which is R times W modulo Q. Also same way, it's just plug in numbers we already have. So 9 times 20 modulo 11, which is 180 modulo 11 is 4. And now we need to compute V. So V is G to the power of U1 times Y to the power of U2 modulo P modulo Q. Okay, this is going to be a little bit bigger, meaning that we have 2 to the power of 5 times 9 to the power of 4 modulo 23 modulo 11. Let's start with the bracket first. So 2 to the power of 5 is 32 again, and 9 to the power of 4 is 6,561. So we have 32 times 6,561 modulo 23 modulo 11. If we do the product of this multiplication, we have 209,952 modulo 23 modulo 11. So we have 11 modulo, no, I'm sorry, we have 9 modulo 11, which is essentially 9. So signature is valid if V is equal to R. So we just calculated V as 9, and if we look on top, R is 9. So the message is valid, the signature is valid, and the receiver can be sure that it is being sent by the intended sender and it is valid, not being altered. And so yeah, non-repudiation, message authentication, and integrity. You can put a check mark on this one. Okay, let's have a summary. After this heavy round of math, we should take a short break and run through some facts. We have three different popular asymmetric systems in place, which is DSA for digital signatures, as we just have seen. Then we have Diffie-Hellman for exchanging keys, for example, which has especially been used in like a hybrid encryption setup. I will get to this in a second again. And we have RSA, which is been used for asymmetric encryption, but also for digital signatures. So you can do both with RSA. And all three are based on the very same concept of public key cryptography, which has been developed by Diffie and Hellman. So Mr. Diffie and Mr. Hellman. And all of those three are somehow based on using prime numbers and using the problem of factoring as an advantage to have an easy one-way function. So it's easy to compute, but it would be hard to re-engineer or recalculate based on the result back to the actual prime numbers. And in order to increase the security, what you can pretty much do with all of those algorithms, you can essentially just increase the key length. So instead of using 2048-bit for DSA, because it's maybe some supercomputer was able to crack it in reasonable time, you just increase the key length to 4096, and this will increase the computational power required to crack a key by I don't know how many dimensions. But yeah, this is pretty much what you can do, because the longer the key, the more secure the algorithm is in itself. And as I said, I would get back to it. The hybrid encryption mode is pretty much the best of both worlds. You have high-speed encryption using symmetric systems such as AES, for example, either as the block cipher or as a stream cipher, depending on what kind of mode of operation you're running. And you have the very secure exchange of keys or messages in general, which you can do on an unsecure network such as the internet by utilizing like one of the three asymmetric systems, DSA, Diffie-Hellman, or RSA. And yeah, most often if you talk about like hybrid encryption, you use the Diffie-Hellman algorithm to do the key exchange in a secure manner, and you then use afterwards AES, probably usually 256 in probably also GCM mode, to have like all possible security features you want with a reasonable key length. Okay, that's it for today's session. I hope you liked the new way of doing the presentation. So instead of reading out pre-written documentations or pre-written statements I want to give per line of my presentation, rather than just talking and do it like more in a flexible freestyle way. Yeah, let me know what you think about this one, and yeah, leave some comments, subscribe to the channel if you like the content, and yeah, have a good day and stay safe.